Thank you for attending this presentation. Recently, there has been an increasing interest in cardiac MRI at a high-performance low-field system due to its reduced off-resonance, reduced B1 plus inhomogeneity, relaxed SAR, and improved device safety and compatibility. Previous studies at 0.35T and 0.55T have demonstrated promising results of cardiac MRI at low fields. For example, this work has demonstrated that a 0.55T scanner can offer cardiac cine images as good as a 1.T scanner in terms of image quality and cardiac function evaluation. The same group has also demonstrated that an optimized BSSFP spiral in and out sequence will have more ISMRM and image contrast than a traditional Cartesian imaging. High-performance low-field system offers new opportunities in data sampling due to reduced off-resonance and prolonged T2, but also suffer more from gradient distortions and concomitant fields. These artifacts are difficult to optimize due to a lack of ground truth data. To fill this gap, this work presents a realistic simulation framework that considers concomitant field effects, off-resonance, and uses realistic coil sensitivities. We also demonstrate 3 applications of the framework in evaluation of artifact and noise level, in optimization of trajectory and reconstruction, and in identification of myocardium perfusion deficit. The proposed simulation starts with anatomical masks obtained from the XCAT phantom. With a set of input parameters, the image contrast is simulated, giving the signal intensity images. The same mask is also used to generate the off-resonance map. A set of coil maps reflecting the actual coil position is generated to obtain coil images for each slice. From the coil images, the signal encoding is performed. We need the case-based trajectory. The corresponding gradient waveform is used along with the slice position to consider the concomitant field effects. The previously obtained off-resonance map is also added into the encoding equation. We use an expanded signal model to calculate for the case-based data, where the concomitant field effects and off-resonance are added into the Fourier coefficient. After we get the case-based data, we can add per sample noise and perform any reconstruction as we want. The first example usage of the simulation framework is to compare the image quality that will be affected by artifact and noise at different field strengths. We simulated cine images at different field strengths and added artifacts one by one. As expected, as the field strength goes up, the concomitant field effects decreases with a more pronounced off-resonance. Overall, at a low field strength, artifact level is lower but noise level is higher. Next, we performed a simulation of real-time 3D cardiac cine at 0.55T, comparing different data sampling and reconstruction strategies. Some of the simulation parameters are listed on the left. Note that this and the next simulation both consider the concomitant field effects, off-resonance, and realistic noise level. The result suggested that with a pseudo-random KD sampling and an extra dimension reconstruction, high-quality real-time 3D cardiac cine is feasible at 0.55T. Inspired by the previous result, we applied the best sampling and reconstruction strategy for myocardium perfusion imaging. We introduced the perfusion deficit spanning 15% of the myocardium, used an ungated continuous equalization, and retrospectively gated the images into diastole and systole. The simulation demonstrated the ability of identifying perfusion deficit at a high-performance 0.55T system. In this work, we have proposed a realistic simulation framework for cardiac MRI, including off-resonance and concomitant field effects. It's flexible in schema model, heart rate, and breathing pattern, and can predict performance at different field strengths, even including non-existing ones. The framework is also extremely useful for optimization of data sampling and reconstruction. By using this simulation framework, we have predicted the performance of real-time 3D cardiac cine and myocardium perfusion on a 0.55T system. These imaging methods were tested feasible with a stack of spiral trajectory and extra dimension reconstruction.